All right, welcome back to another video. Today we're going to look at how we analyze turbulent flow using the modified Bernoulli's equation to calculate, in this case, the fan power needed to overcome the pressure loss. And when you do turbulent flow, we're going to be using the Colbert equation to find the F friction factor, or you can use this Moody diagram. And I'll go through both methods, and I will also post a Octave or a MATLAB code that you can use. You can run it, input values, and get the F value. But let's do this problem, and I'll show you. So air enters a 10-meter long section of a rectangular duct of cross-section 15 centimeters by 20 centimeters made of commercial steel at 1 atmosphere and 35 degrees C at an average velocity of 7 meters per second. Disregarding the entrance effects, determine the fan power needed to overcome the pressure loss in this section of duct. All right, so let's write our givens. We got L is 10 meters, H is 0.15 meters, W is 0.2 meters. We got P1, which is 1 atmosphere, which is 101,325 pascals. T1 is 35 degrees C, or 308 Kelvin. We have V1, which is 7 meters per second. I'm going to scoot up. We got R for air, which is 287 joules per kilogram K. And if we need the other properties like mu, then we can grab those. But for right now, we'll just leave that. We're going to look for W dot. Assumptions. Steady state. Number 2, incompressible. Oops. Incompressible. 3, air is ideal, so we can use the ideal gas equation. There's no pumps or turbines in this section. And we're going to neglect entrance effects. Okay. And then we have the sketch. Just to save some time, the sketch is right here. But you should probably put that on your paper. Okay? So draw out. All right, we got the givens, the find, assumption, sketch, all set up. Now let's start the solution below all of this. Make a heading, and what we're looking for is that power. So W dot is V dot times delta P. We need to use or need to find delta P. We're going to use the modified Bernoulli's. Okay. Spell it out for you. So write it down. P1 over rho G plus V1 squared over 2G plus Z1 plus HP minus HT minus HL equals P2 over rho G plus V2 squared over 2G plus Z2. So there is our Bernoulli's, modified Bernoulli's. Now from the assumptions in our sketch, we can cancel things out. Velocities are the same. Elevation changes are the same because we're looking at the we're looking at the center line of this duct. There is no pump, no turbine. See how you can break things down? So delta P equals HL times rho G. So we need to find delta P. We know G, we don't know HL, and we don't know rho. So let's just find rho first. Oh, let's do purple. Find rho. P equals, we'll use the ideal gas law. Rho RT. Rho equals P over RT. Rho equals 101,325 pascals over 287 joules per kilogram K times 308 Kelvin. Remember, temperature has got to be an absolute. It's got to be Kelvin. We got to make sure our units cancel. We're using pascals, not kilopascals. So the density becomes 1.146 kilograms per meter cubed. Okay, so that's done. We know G. We now need to find HL. So let's scroll down. Find HL. And HL is still the same equation from laminar. This is the given dH over 2G. Okay, so HL equals F times L times V squared over dH times 2 times G. In this, we need to find dH. We need to find a few things. And dH is your hydraulic diameter, which is 4 times the cross-sectional area over the perimeter. So dH equals 4 times 0.2 meters times 0.15 meters. So cross-sectional area over the perimeter, so 2 times 0.2 meters, because there's 2 of those, plus 2 times 0.15 meters, because there's 2 of those. We're finding the perimeter. dH equals 0.17 meters. All right, let's keep going. We have L, I believe we have V, we just don't have F. Okay, so we're going to put a heading here. Find F. And the first thing you want to do is find the Reynolds number, especially with turbulent flow. Oh, actually, you know what? I'll do this. Okay, watch. We'll find F because we need that. Turbulent flow, you'll find out that the Reynolds number, we could calculate Reynolds number and it's turbulent. We're going to use the Colebrook equation. Okay. And I'm just going to show you. I know it's turbulent, but we'll show you because of the Reynolds number. This is the Colebrook equation. It's 1 divided by the square root of F equals negative 2.0 log of epsilon over D divided by 3.7 plus 2.51 over the Reynolds number times the square root of F, all closed parenthesis. This is what they call an implicit equation because you have F on both sides of the equation. And that's what we're trying to find. F is there and F is there. Okay. So in this equation, though, we need to find epsilon over D and the Reynolds number. Okay. Well, let's calculate the Reynolds number first. So find the Reynolds number. RE equals rho V times DH over mu. So we do need mu. So let's go back up and write that in our givens. It's going to be 1.89 e to the minus 5 kilograms over meter times second. And if you want, these are in the back of the book in the tables. Okay. And sometimes if you want, you could label properties. And this is where you can label R, mu, and so forth if you eventually will need those. Okay. Or you can write them in your givens. It doesn't matter. All right. Let me just make sure we're still recording. Yep. Okay. So let's go back down. Let's calculate the Reynolds number. So RE equals 1.145 kilograms per meter cubed times 7 meters per second times 0.17 meters divided by 1.89 e to the minus 5 kilogram per meter times second. And we get a Reynolds number of roughly 72,506. Okay. Or just for reference, 7 times 10 to the 4th. Okay. So we know the Reynolds number. We need to find this epsilon over d term. All right. And we need to use the chart up here first. So let's go to the chart. And we're using steel. So this material, this epsilon, okay, is a material property for the steel. Okay. It's like the roughness. We're going to use 0.025 millimeters. Okay. And we know the diameter. So let's go back. Go back to here. So epsilon over d, which is actually epsilon over dh. We're going to use 0.025 millimeters. We're going to convert that to meters. So let me just do that correctly for you. There's 1 meter in 1,000 millimeters divided by 0.17 meters. So epsilon over dh equals 1.47 e to the minus 4. Okay, or 1.5 e to the minus 4 is fine. Okay. Now, why do we need those values? Well, we got to go back to the chart. This is called the Moody diagram or Moody chart. We can use this instead of that Colbrook equation. So what we have here on the y-axis, we have friction factor. Okay. On the x-axis, we have Reynolds number. Okay. And then these lines here, this one, all these solid lines, is that relative pipe roughness epsilon over d. Okay. So what we need to do is we need to first find our Reynolds number. I got to zoom out here. Our Reynolds number, I believe, was what? 7 times 10 to the 4. So if I go up here, so this is 1 to the, oh, I don't want to, I want to, is that going to do it? Nope. There. This is 1 to the 4. This line is 2, 3, 4, 5, 6, 7. Okay, so we're right there. So let's do a orange line. And we're going to draw a line straight up. Okay. We have our Reynolds number. And then our epsilon over d value was what? About 1.5 e to the minus 4. Okay. .5. So we are from here and here. We're kind of in between these values. Okay. So what we can do, I'll do this, is you're going to follow the pattern of those curves in between. And then once you hit that Reynolds number, you have now, scroll over to the left, that is your friction factor. Okay. So that's how you use the Moody chart. So turbulent flow, you can use the Moody chart or use the Colbert equation, and I'll show you a code that I have for that. But if you want, you could just use the Moody chart. You have to calculate the Reynolds number. You have to calculate this epsilon over D, figure out where they intersect, and then scroll over to the left, and that's your friction factor. Okay. All right. So F is 0.02. So from Moody, F is 0.02. Sweet. Okay, now we can just plug the numbers in. Now, HL equals 0.02 meters times 10 meters times 7 meters per second squared over 0.0. Oh, sorry, the 0.02 was not meters. That was F. My apologies. On the bottom, 0.17 meters times 2 times 9.81 meters per second squared. HL equals 2.94 meters. Now, delta P, 2.94 meters times 1.145 kilograms over meter cubed times 9.81 meters per second squared. Delta P, 33.05 pascals. Now, volumetric flow rate is area times velocity. Flow rate, area is height times width times the velocity. Gives you the flow rate. The flow rate now, 0.15 meters times 0.2 meters times 7 meters per second. Flow rate, you get 0.21 meters cubed per second. And finally, W dot 0.21 meters cubed per second times 33.05 pascals. Your power is 7 watts or 7 joules per second. And that's your final answer. Make sure you box it. So, turbulent flow is very identical to laminar flow in terms of equations, but your F equation is different. We're going to, in this class, use what we call the Colbert equation, which is really you can use this Moody chart, to find your F value. Now, I've also included in Brightspace a Octave or a MATLAB code where you can actually run the code. Okay. You have to enter variables. So you can stop the video lecture here if you are not sure how to program or use Octave or MATLAB. Just go ahead and use the Moody chart. But if you're curious and you have some experience in programming, you can open this up in MATLAB or Octave, enter your epsilon, put your velocity, put your dynamic viscosity, your density, and tell me if it's circular or a rectangle. Okay. Then you don't have to change anything down below. It'll ask you if it's a rectangle, it'll ask you some questions. If it's a circular, it'll ask you what the diameter is. Same with a triangle. Actually, you can do a triangle pipe. Okay. Then what it'll do is do calculations. Hydraulic diameter, Reynolds number. Okay, if it's greater than this, it's turbulent flow. We're going to use the Colbert equation, and then I do some manipulation to figure out how to find F. If it's laminar flow, I just use that. Okay, so watch. I'm going to run the code, and then I got to bring this over. It's going to say enter the width. And I believe, give me a second to what was the width? The width was 0.2. So 0.2. Oh, you gotta make sure you click on it. 0.2. And to the height, 0.15. And then boom, it spits out the Reynolds number and the F value, which was pretty much what we had. So again, if you're comfortable and you want to try it, go ahead. The code's right here. It's in Brightspace. Just download it and open it up. Okay, well, this was a video on analyzing turbulent flow using the modified. Next lecture is on minor losses and how to incorporate those into the system and really the overall system, where now we're going to put pumps or maybe turbines in and figure out what the required power is needed. All right, if you have questions or comments, please let me know. Thank you and have a good day.